Hello and welcome back. So, chapter 3 is vectors, and seems like it might be a little bit of a diversion from what we've been covering because when we started out, chapter 1 was our introduction and all our measurements, and then chapter 2 was the first chapter in kinematics. So, we began studying motion, but now we're shifting over to vectors. And the reason for that is that chapter 2 is one-dimensional motion and chapter 4 is two-dimensional motion. So in order to understand two-dimensional motion, we have to first understand vectors. We could combine it into one chapter and cover what we need to know in chapter 4, but it's nice to actually separate it out first to give you a chance to work with vectors in general to really understand them. And then when we get to chapter 4, you've already mastered the vectors part, and then you can consequently focus on the two-dimensional aspects of motion, because there's some concepts in chapter 4 that even though the equations are going to be relatively the same as the ones you saw in chapter 2, there's still a lot of concepts in chapter 4 that aren't always all that intuitive. So it's good to get the math out of the way and master that first, and then go into chapter 4 and we'll revisit what motion is in one dimension, and then we'll add it to the two-dimensional aspects and the two-dimensional parts where the vectors come in, and you'll start to see why in this chapter here. So here's our outline. Hopefully this will be a good study guide for you. When you go through each of these bullet points here, make sure you can describe what they are and have a relatively good idea of how to solve or problems, or kind of use this as a high-level overview for a test review. So our definitions for this chapter, our first one's a scalar. And we sort of saw that in chapter 2. So a scalar really is a number that has units. So that was 4 degrees Celsius, 10 miles an hour, things that are, again, just a plain number with units. The number can be positive or negative, but again, they give you, the scalar quantity is just really that single number. And again, so we looked at temperature, speed, and mass, or temperature and speed. Mass is another one, so 10 kilograms or 10 pounds. It's basically where the scalar quantity again. But the vector gives the quantity along with magnitude and the direction. So the vector is a little different. So if we looked at temperature, well, temperature is always going to be a scalar. We'll never have really a vector related with temperature. But when we look at velocity, velocity is actually velocity is when you see. Let me put my pen on. When you have 10 miles per hour, so that's your speed, and then you could say north, 10 miles an hour north. So there's your direction right there. So your vector quantity, so your vector is a quantity that gives you a magnitude and a direction. So your speed right here, that's your magnitude, that's your 10 miles an hour, and the direction's north. So if you define your coordinate system this way as north being the positive y direction, and so you're driving north, and then so here you have your positive 10 miles an hour, that's your speed, and your direction's northerly. So if you were going this way here, that would be south, and it would be negative. So then you can put the negative sign right there, and that you could say negative 10 miles an hour. And you wouldn't need to actually say south at this point, as long as you drew your coordinate system. But again, we're going to go back to this word magnitude right there. So magnitude really is this negative comes out, the negative goes away, and we get back to our 10 miles an hour. And then because it's magnitude, we do need now to say south. We need to have them. So it's really a good idea when you're talking about your vector to make sure you do pay attention to magnitude. So even if you have a negative sign right there, when we're talking about a vector, you want to say 10 miles an hour south or 10 miles an hour north. You always want to have that combination. When you're talking about a vector, you want the combination of the magnitude and the direction. So velocity is the vector, and we have that vector notation. We'll get to the notation in a minute. So velocity is the vector, and the magnitude is the speed and the direction. And then when you talk about mass, mass is the scalar, but its vector is weight, and we'll see in a later chapter that the magnitude of the weight is the mass, and then of course you want the direction, and the direction will be downward all the time. But that's something where I'm leaping ahead too much here with the and talking about the weight. But so back to our definitions here. We have our scalar is just our plain number with the unit. The vector is a quantity that gives you magnitude and direction. So velocity is a vector, and its magnitude is speed, and its direction obviously north, south, east or west, or up or down, whatever the context of the problem is. Displacement. So we looked in chapter 2, we looked at distance, and we sort of already introduced a little bit in chapter 2 about vectors, because we said distance was the scalar, and displacement is the vector, and the vector is usually the capital letter. So distance is the magnitude of displacement, and but before we let's go a little slower. We'll build more into that again. So we'll redefine or get back into our displacement and distance relationship coming up. But again, the point here I want to make is that the vector has a magnitude and a direction, and that magnitude is often the scalar equivalent. So when you're talking about speed, that's the magnitude of velocity. When we're talking about distance, that's the magnitude of displacement oftentimes. But again, we'll see further details of that. So to really understand what a vector is and why it's important to have magnitude and direction, our example is we can use the example of the library. And if you just were in the town square and you asked someone, how do I get to the library? Or if you were coming off of Jefferson Station and you wanted to go and you get off the train and you want to know how to get to the Jefferson Library, somebody can tell you, you just go 2 blocks from here. Well, that doesn't really tell you a whole lot. Is it 2 blocks on 11th Street, 2 blocks down Market Street, 2 blocks north, 2 blocks south? It doesn't have any context. Just simply telling you to go 2 blocks from the train station, that doesn't tell you anything. It could be 2 blocks in any direction. So the 2 blocks, or in this example in the slide, a half a mile from here, that's your scalar value. So in order for that information to make sense or to mean something to you, you need to know both the distance and the direction, or the magnitude and the direction. So you need to know how far and in which way to go. So how far is your distance, and in which way to go is your direction. So if you think back of chapter 2, when we said that displacement, we said distance is how far you go. And we said the displacement is how far out of the ordinary, or how far out of place did you go. So how far out of place, it gives you that direction, as well as the speed, or as well as the directional the direction and the magnitude. So when you say how far out of place, you get that distance, how far, and then north. So it gives you both that context of the magnitude, distance, and then the direction of that distance too. So you need to know both. You need to know how far you went for the distance and in which direction. So the appropriate answer for how do I get to the library would be go a half a mile south, or go 2 blocks down 11th Street, down being south, 2 blocks south following 11th Street. So it gives you, the vector gives you a lot more context, and it gives you that magnitude and direction. So the scalar is just numbers with a unit, and the vector is a quantity that gives you magnitude and direction. So the magnitude represents the distance traveled, and is also represents the length of the vector too. So that's important, the length of the vector. So what do we mean by length of the vector? So the vector, when you're drawing something, a vector is always going to be some kind of a line. So you're going to start with your origin, and you're going to draw your arrow. So there's your line, and it has an arrowhead on it. So here's where your origin is, and here's where your end point is. So that could be the line from here to the library. So you're going to draw that line, And you'll see though that you can't always walk in a straight line, but basically the graphical depiction of the vector is the graphical depiction is a line with an arrowhead, and it's pointing in the direction of travel. So you want to start at your origin, and you want to go in that direction right there. So we'll work our way into the magnitude part of that vector. But when we say that it's a half a mile south, you want to have your you want to think about in terms of your coordinate system when you have that, and draw it appropriately big, so that maybe 1 mile is right here, so that half a mile is shown in relative context to the actual picture. Or maybe you want to have it so that 1 mile is out here, 1 mile's here, so you can see it a little bigger, and you got half that distance there. So you want to draw your vector in proportion to what its magnitude is, and more we'll work our way into that too a little more detail. So our notation though, when we're writing these things down, when we're writing, it's going to be a little hard. When you're reading, it's a lot easier. When you're reading in your textbook or you're looking at the slides, it's real easy to type a bold letter R or a bold any letter. R is often used for position, but we use X, and then displacement and velocity, acceleration. So all of our vectors always have that little arrowhead, the half arrowhead on top. And then when we draw it on our coordinate system, we're always going to draw it as an arrow, starting at the origin and ending at your destination. So when you're reading the slides or your textbook, the bold letter with that little arrowhead over it is your vector. And then the magnitude of that vector, the magnitude of the vector, is just simply the letter. Here in this case it's R, and it's not bolded, and it's not italicized either. I'm sorry, it is italicized. The vector is not italicized, but the magnitude is not bolded and italicized, and you no longer have the arrowhead over it. So the letter with the arrowhead is the vector, and then the letter without the arrowhead is its magnitude. So when you're reading something or have printed text, it's real easy to distinguish them because one is bold and the other's not. But when you're writing them, it's hard to make a bold letter versus an italicized letter. They're really difficult to do by hand. So by hand, we always want the notation to look like this. So when we write it, we just simply write the letter by itself. So that's going to be the magnitude. And then this one there with the arrowhead is the vector. So that little arrowhead is really important. The arrowhead tells you it's a vector. The absence of the arrowhead tells you it's the magnitude of the vector, and the magnitude is the scalar. So this is your scalar right here, and then your vector with the arrowhead. So again, the scalar is the number with units, and I'm getting pretty redundant in that. The scalar is the number with the units, and it's also the letter without the arrowhead. So we can have our letter without the arrowhead. The vector is the quantity with magnitude and direction, so that's the one with the arrowhead on it. And it answers the question, the vector answers the question, again, how do I get to the library? So graphically looking at that, if you're standing in the town square right here, or you're at Jefferson Station, and it will just stick with the town square here, and we say we want to go half a mile. So again, that could be half a mile this direction, it could be half a mile here, it could be anywhere. You could be kind of spinning around right there, not really knowing where exactly the library is. But it could be anywhere in that half a mile radius. So in order for it to mean something to you, you need to know how far, which is the distance, and then in which way, that direction. So half a mile south means that here's the library right here, half a mile south. And you see here the coordinate system is built right in, and we could put it separately right here, with that being north and this being south. But we saw it built right into our picture here. So going half a mile south, that gives you more context, and it tells you exactly where the library is and how to orient yourself to get there. So half a mile south, let's explore that in a little more detail. So in this picture, it's real clear cut. Going half a mile south, you're standing right in the middle of the intersection or in the middle of the town square, wherever, and you obviously can go clearly north, east, south, or west. And in the picture, in the circle, this picture here, your path is unimpeded, you're uninhibited. You're standing right in the middle of the intersection, and you can clearly walk that way with no obstacles. Same thing here. Even this way right there, you'd have no obstacles in your path. But that's not always true. So if we were here on the Jefferson campus right here, we can see that this one right here, we can see here's our Thomas Jefferson University right there, and that's actually the one on It's on Walnut Street. So that would be the college building right there, and then over here, or no, sorry, that's not the college building. Actually, I'm not sure where that would be. That's probably the neuroscience hospital right there, because here's our 11th Street right here and 10th Street. So this is Eakins Oval right here. And then on Walnut Street, here's the front of the library. So here's the library entrance right there. So if you got off of the, let's say you got off of the, say you took the Patco train in and you came in at 10th and Locust right here, and you wanted to know where the library is. You can't really see it from when you get out. Actually, that's where the neuroscience hospital is. So when you're down here and you get out of the Patco train and they say, well, you just want to go right through that square. If you want to go right through here, well, there's a building there. There's the neuroscience hospital, and when we're on Locust Street, one of these is the residence hall, isn't it? And I think Jimmy John's is back here somewhere, off of Locust, and I think or 11th and Locust down in this way somewhere down here. So you got buildings in your way. You don't have that nice, neat, clear path. So you're gonna have to walk a little bit if you walked along here, and then you walked along here to get to the library. So there's your vector. Let me rearrange it. Let me erase that a little bit, make that a little neater. So you get off of the Patco station right here. So that's your origin right there. So you're getting off, and you want to walk to the front door of the library to get in. There's only one way to get into the library. So there's your front door right there. So you know that there's buildings here, whether this is the neuroscience hospital here, and then if we go up to a little further over, another block is that Jimmy John's in the Hamilton building, and then here on the front of the library, the two residence halls are right here. So, and then right in the middle is where you want to enter to get to the library. So you can't walk through those buildings. Now your direct line is impeded. You have a lot of buildings and a lot of things in your way. So you no longer have that real nice, neat, straight line that you can walk in. So you got to go this way. You got to walk down the street here, and you got to turn. So there's a right triangle. We just made a right triangle there, and here's our right angle. So that right triangle, that's going to be our best friend through the rest of this semester. We're going to find right triangles in everything we look at, except two chapters. When we look at rotational motion, we're not going to care about right triangles there. We'll have a sort of an equivalent. So pretty much this whole semester, we're going to be looking for right triangles everywhere, and especially every time the reason for that is we're working with motion. So motion, we're always going to have to figure out a way to go from here, our origin, to there, to our destination. So we're always going to be looking for a way to go from our origin to our destination, and we don't always have that straight line. We don't always have that nice, neat path to get there. So we have to break our path down into the components. So we walked, we don't have our legend on here, and I'm pretty sure when we go from Locust Street to Walnut Street that's heading north, and then this is south, and here's our east. Actually, that would be west, actually, going from, I think, going in, or no, I'm sorry, that is east. Going the higher numbers is going west. So we have our little triangle there, and we're going to walk north a little bit, and then we're going to walk west a little bit. So that's where we kind of come into this. So where we kind of come into these component discussions. And if we want to stick with our numbers, we got to walk, if the library is 1.5 miles northeast, you might first have to walk east and then walk north. So you resolved your components into northeast, south, and west, or like we did here. Here's our north and then our west. So you walk north and then you walk west. And if we wanted to use these numbers here, for example, if the library is 1.36 meters east and 0.634 meters north, what we ended up doing is we now went from our map picture. We went from our drawing on our map back to drawing on our coordinate system now. So in this picture right here, we're saying that the library is 1.5 meters from the origin, from your origin over to here. So there's the library right there, or the entrance to the library. So our distance R, our distance R is 1.5 meters, and then our vector R is 1.5 meters in some combination of X and Y. And we don't really know that yet. And other than when we look here, we have our theta 25 degrees towards the Y direction. So if we made that north and we made that west, we would say 25 degrees northwest. So our vector is 1.5 meters and 25 degrees north of west. But that's still, we've got our 1.5 northwest. And so we can still even leave out the 25 degrees at this point. It helps us north of, where the 25 degrees helps us a little bit north of west. But what really helps us a lot more, it makes a lot more sense, because obviously we can't figure out, it's a little hard to figure out walking 25 degrees north of west. So what's a little more helpful is these components right here telling us to walk 1.36 meters in the west direction, and then 0.634 meters in the north direction. So that helps us a little bit more. So what we did was we took our vector R and we resolved it into a Y component and an X component. So the X and Y are scalars. The R sub Y and R sub X, they're the scalar components of the vector R. So our vector R gives us our, in a little more generic terms right here, we have any vector A. Any vector, you can put any vector there, A, and it's broken always down into its Y component, or not north, broken down into its Y component here, and its X component, and here's our coordinate system that tells us that. So we always need to put our coordinate system, and we always need to start our vector at the origin and end at our destination, and then we can fill in that right triangle right here. So there's our right triangle, and we have our vector A and our components A sub X, that's A sub Y over here, and A sub X right here. And then our angle right here, is always with respect to the X direction. Always. You want to remember that. The angle is always from the X axis right here, the X axis. So even if you drew your vector that way, you got to figure out the angle here, and then of course you can put the difference right there in that place. And of course we'll do a lot of examples with that as well. But back to our length, our angle, and our components, they can be calculated. The values, the one, if we knew that this is 1.5 meters, or we saw in the last slide 6.35, 1.36. So what we do here is our values are the R sub X or the A sub X, whatever they are, we wind up with our X and Y components. And so to calculate those, our theta value is always the inverse tangent, and that didn't come out right on our slides. So that should be theta is the inverse tangent, and that's written as a superscript -1 of A sub Y, opposite over adjacent. So here's the opposite, and here's the adjacent. So if you think of that as if you think of your tangent as the opposite, the side opposite the angle, and the side adjacent to the angle. So a sub x is the component that's adjacent to the angle, and a sub y is the component that's the opposite side of the angle, the opposite part of the angle. And so here's our angle, and here's our opposite, and here's our adjacent. And then the components themselves, a sub x is a cosine theta, and a sub y is a sine theta. And then so these are magnitudes again. So if the vector a is 1.5 meters up to this point here, then a over here is 1.5, and then to get the value of r by itself, the magnitude of r, we use Pythagorean theorem, and that's this one right here, Pythag theorem, and that's the square root of r squared plus r sub x squared plus r sub y squared. Another way of writing that is r squared equals r squared equals r sub x squared plus r sub y squared. So I think I jumped a little bit ahead. I want to get back, and I should have been following along on the computer with my slides. I can't see the slide numbers here, but I think I want to get back a little bit. And oh yeah, I did. I wanted to do a little calculation, so I'm going to go back. I want to come back over here, and I'm going to show you this slide right here. So, and we want to use that in conjunction with our trigonometry equations here. So, what we can do is so I want to see if these are actually equal to each other. So, to show you that both the A and B are equal, we'll use our trigonometry. We'll use our trigonometry equations. So here in figure A, move this a little bit bigger here. So in figure A, we know the vector and we know the angle. So in our problem solving, I'm sorry, scalar and our angle. So in our problem solving, we want to write down what we know. So so here we have our value of r equals our 1.5 meters, our theta equals 25 degrees, and then our equation here to calculate the components, to figure out what the components are, is that we're gonna have our equations. Run down over here. Our equations on this sheet here. So our trigonometry, our a sub x is a cosine theta. So, a sub x is a cosine theta, and a sub y is a sine theta. So now we can go ahead and plug our numbers in because we know that a equals, I should put this as an A right there, just for consistency. So we're going to make this an A since I already wrote those instead of R. So A is 1.5, and cosine of 25. And then this one here is 1.5 because that's what the value of A is, and the sine of our angle of 25 degrees. So cosine of 25, we plug that into our calculator. Cosine of 25 is 0.906. We won't round that until we get our answer, and then we'll multiply that by 1.5, and that gives us our 1.3. It's on our calculator, it's 1.3594, a whole bunch of numbers, but we want to remember our significant figures. And we see right here, this one right there gives us 3, and so does this. We have 3 significant figures. So it's 1.359, so we want to look at that fourth digit, and the 9 tells us to round. So instead of writing 1.35, we'll write 1.36, and that's just what we got down there. And then when we solve the sine, we'll do 25, the sine of 25, 0.422, etc. And we multiply that by our 1.5, and we get 0.63 and a whole bunch of numbers again. But our four numbers are 0.6339. The 9 again tells us the round. So instead of 0.633, we do 0.634. So this equals 0.634. And that's what we got right there. So our numbers, so when we took our trigonometry values right here, we tried it with using A, and we have our right triangle right here. So here's our A sub x and our A sub y right there, and A sub x over here. And so when we broke it down into our components, and then we used our trigonometry equations, we see that we got the same answer in B. And then we can work in the opposite direction now. We can look at figure B and say, well, okay, we have these components right here. Are we going to get, if we use our trigonometry equations, are we going to come up with 1.5 as our vector? So the way we want to do that, so to figure out if r equals 1.5, we would use our Pythagorean theorem. So r equals r sub x squared plus r sub y squared. So our value over here, r equals the 0.634 squared plus our 1.36 squared, and then we take the square root of that. So when we take 0.634 and square that, we get 4.019. So we'll put that as 0.402, and then we'll square our 1.36. It gives us our 1.8496, and we'll add that to our 0.402, and then take the square root. And when we take the square root, we get 1.5005, a whole long line. But we just want to look at the 4. We know we want 3 digits for sig fig. So the 4 digits, when we take this, when we square that, take the square root of that, we get 1.500. And looking at the fourth one, we don't need to do anything. So we wind up with, we'll just drop that off. We don't need to round up or down. And so since it's a 0, so we get our 1.50 meters. And that's what we have right over here, 1.5. So we see we can go either way with that. We can both of these figures, figure A and figure B, are equivalent representations. They're both telling you that you're going 1.5 meters in a certain direction, and that direction is going to be a component or divided into an x and a y component. You're going to go 1.36 meters this way and 0.63 meters that way, or 25 degrees towards the y direction with reference to x. And we are 25 degrees there. And we could have done our theta is equal to our inverse tangent of opposite over adjacent, or y, r sub y over r sub x. And you can do that. You can check that out too to see that we'll still come up with 25 degrees using those numbers. So we have our trigonometry equations, and these trigonometry equations, you want to really, and you'll probably start, if you don't already remember them or know them, the more you go through the homework, the more you're going to use these, and consequently you'll start to have them memorized. But it's a good idea to try to commit them to memorization anyway. They're going to keep coming back all semester long. So here's our component vector again, and I could have done all that writing on this slide, but again here we walked our 1.5 miles to the library, and to answer if A and B were equivalent, you use those trigonometry equations on the last slide, and then you see here to find R, you use Pythagorean theorem, and more information is on that in Appendix A of your textbook. And basically the Pythagorean theorem equation is this one right here. And then you couple that with the directionality to find your theta. So typically our vectors are always going to give us, we're going to either be told the magnitude and the direction or the components. So when we're given the magnitude of the vector and the direction, the direction is always going to be theta. It's always going to tell us the theta is always going to tell us the directional part. And again, theta is always with respect to x. So it's always going to be some number of degrees towards y, or elevate it in the positive direction away from x, or it could go this way too. Either way, again, we'll see that context in a little bit, but it's always the angle or the direction is always with respect to the x-axis. So you're always going to draw that angle starting on the x-axis and then going either up or down. It'd be going up this way or down this way. And that calculation of theta, if you're not given it, so here in A, you're given the magnitude and the direction. So you want to find the components, and you want to find the components by using the cosine theta, the vector r, in this case cosine theta, or r sine theta. So that's your option one, or problem one. When you're solving the problems, this is the first type of problem where you're given the magnitude of the vector and the direction. The other type of problem is when you're given the components and you're told to find the vector and the direction. So you're going to be told to find the vector and find the magnitude of the vector and the direction in which you're traveling. So in that case, when you have to find your unknowns now are the vector and the angle. So over here, the unknowns are the components. R sub x is unknown, and R sub y is unknown. But in B, R sub x and R sub y are given, and you want to find the vector and the angle. So when you want to find the vector, the magnitude of the vector and the angle, you use Pythagorean theorem. So you're going to use equations 1 and 2 right here for figure B. And so either way, they're the two types of problems you're going to look for. In one case, you're going to be given the vector and the angle. In the other case, you're going to be given the components. So how do you determine the correct sign of the components? So you have your vector, your vector's in blue over here, and here in the one case, in the one case here, you got your vector still starting at the origin. You're starting at the origin, and then you're going into a quadrant down here. So that means when you draw your right triangle, the x component is greater than 0, so that's going to be positive, and the y component is going to be negative in that case. And then in figure B, when here's your coordinate system again. Now figure B is going in this direction. Here's your right triangle. So in this case, a sub x, that component is negative, and the y component is also negative. And then in C, we're starting at the origin again and going to your destination. But here, the y component is positive and x is negative. And then over here in the last case is x is positive and so is y. So that's how you find the correct signs of the vector components, by basically looking at that right triangle again, and that helps you to tell where the components are. But then when you're using your calculator though to determine the angle, you need to be careful though, because when you determine the angle, your calculator is going to get a little going to kind of in some cases give you a funny answer. And the package I use for these presentations is it's called Explain Everything, but when it imports degrees, it doesn't always import them correctly. So that's this is 180 degrees, and so we want to be careful when using our calculator to determine the direction of the angle. We may need to add 180 degrees in order to get the correct angle. And an example of that is if you have an a sub x value that's negative 0.5, so and an a sub y that's a positive 1. So let's find that on our picture down below here. So a sub x is negative. So here's a negative a sub x, and here's a negative a sub x. A sub x is negative right there and negative right there. But then a sub y is positive. Well, that's not here. A sub y is positive, and a sub x is negative. So that's this picture. We have our negative 0.5 and our positive 1.0 meters. So when we calculate theta, it's opposite over adjacent. So theta is going to be the inverse tangent of the opposite over adjacent. So it's going to be our a sub y over our a sub x. And a sub y is positive 1. A sub x is our negative 0.5. So when you put that into the calculator, you end up getting an answer of negative 63.4. But that doesn't make sense. When you look at figure C here, negative 63.4, there is no such thing, because this is 0 and this is 90, this is 180, and this is 270, and then 360 right here. So 63 degrees falls over here. But there, as you can tell, there's no such thing as a negative 63. But in order to get that negative part, what the negative is telling you is that you should be in this quadrant over here. And but to get the right number, we know we need the number between 90 and 180. So that's why you got to add the 180 degrees. So when you add 180 degrees to the 63.4 degrees, that should be a degree also. And if you're following along with the slides in the PowerPoint, they're giving you the PowerPoint slides have the degree symbols in it. It's just on the presentation, the recorded one. So when you add that 180 to the negative 63.4, you get a positive 116.6. So that's more like it. That means you're going from your angle over here is you end up getting your angle of 116.6, and that puts you right in between. It's greater than 90 and less than 180. So the example sketched again, our numbers up here put us in figure C, and then that 116 is more reasonable. Puts it in the correct quadrant right there. So the correct answer for our angle is the 116.6, and because our angle we always start on the positive x-axis and make our angle that way. We would report the 116. Technically, we could say that the 63 degrees is there. It's the difference between the 180 and that 116. But in sticking with our notation that requires that the angle be from the positive x-axis, we get that 116 as the direction, as our theta, or as our angle for direction. So our quadrants and angles, again, just to keep in mind, this should be a refresh here, where our first quadrant is between 0 and 90, second quadrant between 90 and 180, third quadrant between 180 and 270, and then the fourth quadrant is between 270 and 360. And so our first, another problem to look at, now that we looked at our directional problem with the library, but this time we want to look at the problem here where we have a baseball. We're looking at we're in the press box at a baseball park, and we're 44.5 feet above ground. And then so a reporter in the press box, the reporter is in the press box looking at an angle of 13.4, and again that should be 13.4 degrees below the horizontal to see second base. So we want to know the horizontal distance from the press box to second base. So our first instinct, we know that we need this right triangle, and so the first part of our problem solving is we want to write down what we know and what we don't know. And then we want to also draw our pictures and make sure we put our coordinate system on there too. So we have this press box is 44 feet above ground. So we can go right into our drawing. We can start our drawing right here. Or actually, let me make room for a press box. So here's our press box. And it's 44 feet above ground. So ground is our origin. So that's our origin. And here's our 44.5 feet above ground. So that we'll call that our R vector, our distance vector. And then the reporter is looking at an angle below the horizontal. And so below the horizontal to see second base. So if we went and did that and said second base is right over here, we would have our angle right there. But that's not the correct drawing because it's below the horizontal to see second base. So that's not correct. So we want to come back up here and we want to say, well, here's our press box. And we're still going to draw it. And we're still going to say it's this distance right here is 44.5 feet above the ground. So we can still call this ground. We won't yet call it the origin. We're going to call that ground. So when we do that, so we want to look at our next part and say draw our horizontal right here. So you're in the press box right up here. If you're in the press box right there, and the angle is 13.4 degrees. Well, that's not right either. So we didn't want to do it that way because that's the right triangle. So this is our right triangle. Ooh, erasing too much there. So this is our right angle, and basically what we're saying is we're looking. This guy's looking at, or the press box. The reporter's looking towards second base. So there's our vector, and here's our second base right here, and then here's our horizontal. So we now got rid of our right angle, so we want to erase that part there, and so we want to put back our height vector, and then so we got our height in there, and now we have below the horizontal 13.4 degrees below the horizontal. So here's our horizontal. So now we can finish our right triangle, and our right triangle is just basically taking this part right there and moving it over here. It's an equivalent. We're allowed to do that, and because obviously we drew it to scale. You can see that they're the same heights right there. So that's our real triangle, and this is our origin, and our origin can still be at the ground. We can still do that. So we can, if we wanted to clean up our picture, we can erase this part right there. So this is why drawing a picture is helpful. It's always helpful to draw everything out because you have your press box, and then you have from your horizontal down. So you drew your distance vector or displacement vector right here, and you got your angle right over here, and then you got the one component, the 44.5 above ground, and so now the last sentence is, what is the horizontal distance from the press box to second base? So what we can do here is our unknowns, again, are the horizontal and the resultant, the horizontal distance, and then this resultant right there. We don't know. That's an unknown. And this horizontal distance, if we want to call that d sub x, that's our unknown. But d sub y is 44.5. So what we can do is we can first make more room. So now that we have a little more room, what we can do is, we know that the tangent of an angle is the opposite over the adjacent. opposite over adjacent. So that's y over x as our opposite over adjacent. So again, the opposite side of the angle. So we know that, and we know our angle, but we want to find. We know our angle is 13.4, and then we know that the opposite side of the angle. So here's our angle 13.4, and the opposite side of the angle is the y value, and then we don't know what x is. We don't know that. We don't know that component right there. So we don't know the d sub x. Another way we can write that is putting d sub y and d sub x right there, our components. So we want to find x. So we want to rearrange this. We want d sub x, and then that'll give us our d sub y over the tangent of theta. So now we can plug numbers in. We can plug in our d sub y as our 44.5, and our tangent of theta is tangent of 13.4 degrees. So that gives us a value of x. It gives us a d sub x equal to 187 feet. So now we have this horizontal distance. That's this value right here. This d sub x is 187 feet. So that's our horizontal. What is the horizontal distance from the press box to second base? So and that's all it asked us for. So that's the only thing we have to do is solve for that horizontal distance, and it didn't even ask us for the vector. We could actually go ahead and find that. So this vector here is so that value d. So d is equal to, or we don't want to put the vector right there. So d is equal to d sub x squared plus d sub y squared. So it only asked us for the horizontal distance, but if it asked us for the magnitude of the vector, you would find that with Pythagorean theorem. So your d sub x would be your 187 squared plus your 44.5 squared, and that would give you your value of d. And then this one is asking for the positive, find the x and y components of a position vector of magnitude r if its angle relative to the x-axis is 32 degrees. So that's a little more straightforward than our press box one. This is a pure vector analysis issue. So we want to draw our coordinate system. Oh, sorry about that. So we want to draw our coordinate system, and so we have this will be our positive x, and this is our positive y, and then we want to find our x and y components. So there are unknowns. That's what we don't know, and that's what we don't know is what we have to solve for. Except in the last case, we did not know d, and it did not ask us to solve for it. For an exam question, that press box question could be exactly as it's written, plus saying find the magnitude of the displacement vector, or find the magnitude of that d sub x. So you would do the whole solution. You would use your Pythagorean theorem in that case too. So for this problem, though, it's just finding the x and y components. So we have our position vector is 88 meters. So our position vector has to start at the origin, and it has to end at 88 meters. So that's our position vector r. And then the angle relative to the x-axis is 32 degrees. So we know our position vector. We know theta. We don't know r sub x, and we don't know r sub y. So they're the two things we need to find. So we want to solve for them, and our trigonometry equation r sub x from our last a few slides back is r cosine theta, and r sub x or r sub y is r sine theta. So we can now go ahead and plug in we also know that our magnitude of r is 88 degrees. R is 88 times the cosine of 32 degrees. And down here, ry is r, which is 88, times the sine of theta, which is 32 degrees. And this first one comes out to 75 meters, and this comes out to 47 meters. And I think our next problem is similar to that too. So we have a vector has a component a sub x and a sub y. So we want to draw our coordinate system again. So we want to draw our coordinate system, positive x and positive y. And we know that a sub x is 22 meters, and we know ay is 13 meters. And what is the magnitude of that vector? So our vector is going to go this way, and it's a vector a, and we don't know what it is. And what angle does the vector make with the positive x-axis? Theta, so we don't know that either. So we're given ax and ay, so that means we can use Pythagorean theorem, and that's square root of a squared sub x plus ay squared. So we can go ahead and plug in, right now. And we have 22 for a sub x. We want to square that. And our a sub y is 13. And we want to square that. And it's always good convention to keep your units in there. So I got a little sloppy there. So you want to keep your units in there. And so when you go ahead and solve that, it comes up with a value of a equals 26 meters. So if you don't put your units in here, it's real easy to forget to put them there. So that's why you really want to keep those units there, keep them going forward. And then to find our angle, we have our tangent of theta equals our opposite, the side opposite the angle, over the adjacent. That's our opposite and adjacent. So again, it's the side opposite the angle, and that's our y component, and then divided by the adjacent side, the side of the triangle that's adjacent to theta. And so now we can plug in our values, but we can't, because we don't want the tangent of theta, we want theta itself. So theta itself becomes the inverse tangent of that opposite over adjacent, that a sub y over a sub x. So now we can substitute. Now we can put our numbers in. And we get our tangent inverse of 13 meters divided by 22 meters. And the inverse tangent of that amount is, erase that here. So that our theta value now is 31 degrees. So we found our magnitude of that position vector, and we found the angle, and the angle is the direction. That gives us the direction. So a little bit about adding and subtracting vectors. We can add them graphically by placing the tail of the second at the head of the first. So that's always something to keep in mind. You can see the picture here where the head to tail is right here, head to tail, and then they're all vectors. So the value of D, when we know what A, B, and C are, D is the sum of those together there. So that's pretty straightforward. So it's just in this case, if we think of this problem, if we look at this problem right here, we found the vector A, and we found this vector A. And if we found all the other ones, we would just sum them together to find that vector D. And then adding and subtracting vectors. So that's what we're really going to be doing a little bit of actually. And the way we want to do them, if we just know the vectors, we can subtract them just like we added them in the last case. But more practically, we're gonna know the components. So when we use the component method, we just find the components just like we did in problem number 9. We found the components. Problem 10 gave us the components. So we either find the components or use the components given. And we got to make sure, though, that when we're adding them by component, it's always the x values that we add together and the y values that we add together. So if these are our three vectors, a, b, and r, so if vector r is vector a plus vector b, so when we do them by component, r sub x is the component sum of the vectors a sub x and b sub x, or a and b. And then same thing with r sub y is the y components of the a and b vectors there. So when we find them that way, and then we go find the result, and we would use Pythagorean theorem, and here's our x component and y component, and then that tangent, inverse tangent of opposite over adjacent to give us that angle. To add and subtract pictorially, or just without the knowing the components, if we're just drawing them there, we're drawing it as though we're treating them as a bunch of we're finding that overall resultant right here as though we're treating each individual as a right triangle. So we found our right triangles there, and we found our components, and then that gives us this overall large vector right there. So either way, we end up with three right triangles, right? Three right triangles, and then the overall right triangle here. So that right triangle again, we just got to keep looking for it in everything. And so subtracting vectors, subtracting, what we're really doing is adding a negative. So subtracting a vector, the negative of a vector is a vector of the same magnitude, just pointing in the opposite direction. And it's the same as saying a minus b is a plus a negative b, where the negative b is going in this direction. It's here's our b vector, and the negative puts it in the opposite in the opposite way, or opposite direction. So the negative of a vector is represented by an arrow of the same length as the original. So b and negative b are the same lengths, but they're just going to point in opposite directions. So it's like taking this vector here, b, and multiplying it by a -1. When you multiply 9 times 1, you still get 9, or 9 times -1 gives you a -9. It's the same thing here. B, our positive b times a -1 gives us a negative b. And because we're talking about vectors, we're reversing the direction of that vector. So unit vectors are going to become really important in a later chapter. I think it's 7 or 8, when we talk about momentum. So unit vectors, basically what they are, and we'll refresh this when we get to that chapter too. So a unit vector is multiplying by 1. So when we look at this one here, and we say we multiplied by a -1, we multiplied by a unit vector of -1, by unity. So 1 is often called unity because it doesn't change anything. It's our basic unit, or unity, equilibrium length right here, and its purpose is to tell us direction, though. Like, why do we want a unit vector? Its purpose is to give us that direction. So in the last example, multiplying by that -1, it told us to reverse the direction. So we have b up here, and we reverse the direction of -b. Well, in this case, our unit, this would be 1, and this would be 1 right there. So we have an x value of length 1 and a y value of length 1. And then we can have a we can have a vector that's 3 units. So if we did that, we have 3. So I obviously don't draw to scale very well, but that would be 3 units. And it's similar to multiplying by 3. So our unit part, when we said earlier in one of the slides that when you draw your vector, you have to draw a proportional. So if it tells you that you have a vector of 1 unit and then a vector of 3 units, you have to draw the 3 unit vector longer than the 1 unit vector. So you have to draw the vector in proportion to its size, and you have to indicate that which one's longer than the other. So in the one case where we had the x value was 1.36 and the y was 0.63, we want to make sure that we're not drawing it so that the triangle looks like this. That's 0.6 and 1.35 down here. Obviously, 1.35 is bigger than 0.6. So we want a long one here and a short one there and a short y. So this would be 1.36 and this would be 0.6. So they're in proportion to each other. The x is obviously a lot longer than the y value. So we want to make sure that we're drawing our triangle, not a perfect all sides equal triangle. That's not going to be ever reality. We want to draw all the sides and the vector in proportion to its actual size. So again, the 1.36, that vector or that length has to be a lot longer than the y side of 0.6, and then consequently we get a vector of 1.5. That's going to be a little shorter or a little bit bigger than the x component and a whole lot bigger than the y component. So we have, again, our unit length or unity is 1, and we can have 3 units, we can have 5 units, 10 units, any multiple, even a fraction of a multiple, like 1.36 is saying that we have 1.36 unit lengths, 1 unit length plus 0.36 unit lengths. So again, our unity, and where this all comes into play, or what makes it important, is that when we talk about our x and y components, so we know right there that we're talking about the y component of r and the x component of r. But when we start plugging numbers in, when we say 0.36 plus or 0.6 plus 1.36, we lose the directionality. So we can say 0.6x, and actually let me write that a little better. So when we're talking about r sub y plus r sub x, it's really obvious that we're talking about the y and x components. But when we put numbers in there, when we say 0.6 plus 1.36, well, now we lost the direction. We just have our magnitudes, but we no longer have our directions. So we can say 0.6, and we'll put that little y caret, plus 1.36, and that's, sorry, let me write that better. So we can say our 0.6 y plus our 1.36 x. And that's what these are, the little x and y with the caret top. The little caret top, it's not the vector, it's not the arrow that goes on a vector. It's the little hat, that little hat or little caret top or caret, whatever word you want to use. It's that pointy end, that little top, the little hat that sits over it. So it's not indicating a vector. That's what this symbol does. That indicates a vector. But the little hat is it represents our unity. So that means unit, or unit length, or unit vector. So unit vector, it's dimensionless, but it gives you the direction. It tells you the y direction and the x direction. So that's why they're important, and they'll come back again in later chapters. So here's our proportional length again. Here's our 1. This is our unit length of 1. And then this is our 3 times that length, 3 times a, negative 3 times a. And again, the scalar can be any value. So where this all comes into play again, tracing it back to chapter 2 or 3, or I'm sorry, 2 or 4. So a two-dimensional coordinate system gives you the x and the y axis. And the position vectors, if we use r sub I is the initial point or the initial vector, r sub f is your final. So you can say that your delta r, your delta r, it's not r. So r starts at the origin and goes here. So here's where you began, and here's where you end it. So if you began over here, you didn't begin at the origin. If you began there and went and you if you went from your initial to your final that way, if you didn't start at the origin, you would find a delta r. You would still do your vector r sub I from the origin to where you began, and then from the origin to where you end it, and then find the difference between the two. Yeah, so that's your displacement. So this would be distance, this would be distance, and this delta r is your displacement from the two heads, from your initial starting point and your final starting point. So so again, and then there's our right triangle. And then when we look at velocity is a vector, and our average velocity, here's our vector right here, and it's another vector, our displacement vector over time. And but we see though that VAV and that our average velocity and our displacement, they're pointing in the same direction. They're always going to be in the same direction. So if you start here, this is where you start and you end. So when you start here and you're walking, you're moving. So you're in motion now, going from 1 to 2. So of course, when you're moving from 1 to 2, your velocity is going to go in the same direction. If your velocity went that way, there's no way you can walk forward. You can't walk forward at a backward speed. So you can only walk forward at a forward speed. So V average, or your velocity, is in the same direction. If you turned around and walked that way, then your velocity can be in the negative direction. But then you have to be in the negative direction also to have that. So when you're in motion, the direction of motion, your velocity, your direction of motion, your displacement vector is going to be in the same direction as your velocity, because again, when you're moving from point A to B, you're moving at a velocity. You have a speed and a direction. So your direction's this way. So your speed's going to be that way too, and consequently your entire vector is going to be in the same direction as your displacement vector. So that brings me to a proportionality example here, where proportionality is oftentimes a question on the MCAT, like what happens to one value when you change another value. So here in this equation 3,3, we're looking at our velocity vector, and it's directly proportional to r. So they're on the same plane. We're saying that v equals r, but it's v equals r divided by t. So v average is related to 1 over t, 1 over delta t. So they're inversely proportional. But v average is related directly to r. So they're directly proportional. It's more like a 1-on-1. So a good way to see what happens when you increase the time or decrease the time, what happens to the speed. So it's always nice to put numbers in that are easy to work with. So we know that the number 8 is equal to 4 times 2. So that's a nice, neat set of numbers here. So we can say that 8 divided by 2 equals 4. So this would be our average velocity. This would be our delta r and our delta t. So what happens to velocity when you cut your time in half? Would you need to speed up or slow down? So if you cut your time in half, you're dividing this by 2 and you get 1. So that means you have to multiply this by 2 up here. So if you now divide 2, if you cut that in half, that gives you 1. So 8 divided by 1 is no longer 4. So your velocity, if you cut your time in half, your velocity is going to have to double. So we double our 4. 4 times 2 is, or 4 plus 4 is 8. So same as 4 times 2 is 8. So we're back to still maintaining 8 up here. But when you reduce this one by 2, you got to increase the this one by 2. So they're the inverse relationship. The inverse relationship is when you have that, you got to double this. If you cut this one in half, then you double this to keep that proportion. But if we were talking about V and R with so if we go back to our example of V and R, we'll put that a little neater now. So if we look at V and R, so if we have again 8 is or no, sorry, we didn't say that. So we have 8 over here divided by 4 equals 2. So so if we want to look at, or actually let me make that a number that's easier, a little easier to work with. So 8 divided by 2 is 4. So, oh, that's the one I already had. No, we want to say, sorry about that. We want to say that this is the number 4. This is 4. And this is 2. So, so this is our velocity, our vector r, and our time, our delta t. So if we want to look at v and r, they're directly proportional to each other. So this is going to stay constant. So if we cut 8 if we cut that in half, if we cut that in half and we make that a 4, then what happens with our 2? So we're going to have to double that as well, and to make that a 4, and then we end up with, or I'm sorry, we have to end up cutting that in. So if we cut our 8 in half, if we cut that in half, we get a 4, and 4 over 4 is 1, not 2. So that means we have to cut that in half as well. So when they're directly proportional, what you do to one, you do to the other. If you cut this in half, you got to cut that in half. So if you divide this by 2, you get 4, and 4 over 4 is 1. So that means you got to divide this by 2. So 2 and the 2 gives you that 1. So when they're directly proportional, if you cut something in half, you cut the other in half. If you double something, you double the other. But when they're inversely proportional, if you cut it in half, then you double. So you get this relationship. You get one gets cut in half, the other gets doubled. But when they're directly proportional, it's a 1-to-1 relationship. You double something, you double the other. You have one, you have the other. So we're going to work on that throughout the semester. We're going to have a lot of these proportionality problems that we'll work on together to make sure we reinforce that. And you can expect the concept questions. You can expect quite a few concept questions asking what happens to one parameter when you double or halve or divide something by 4 or multiply it by 16. But remember that when they're directly proportional, if you double one or multiply it by 16 or divide it by 4, that's what you do to the other one. When they're inversely proportional, if you divide by 2, you multiply the other by 2. So we'll work on those more and more problems with those. So back to our position, displacement, and velocity. Our instantaneous velocity, that vector is the tangent to the path, and the magnitude is the speed, and that's a scalar. So we just want to reinforce in this slide here again that tangent right here being a vector. So that tangent is a vector, and it's the instantaneous velocity vector. So the velocity vector has a magnitude, which is your speed, and then the direction, which is that angle. And velocity again tells you how fast the particle is moving. That's its speed, and in what direction, and that's going to be the angle. And then your acceleration is also a vector, and acceleration vector is the direction of the change in velocity. It's the direction of that change. So these don't always have to be in the same direction. The direction of change, when you're slowing down, you could still have a positive velocity, but your acceleration, you can still be moving in this direction and slowing down, but that means you're decelerating. So V and A will be in the opposite direction in that case. So the velocity vector is always in the direction of motion. but the acceleration vector can point anywhere. It can point in any direction. And to understand that, we're going to look at our little roller coaster slide again here. It looks like a roller coaster, but really what the way you can think about it is more like blood flowing, because if it's a roller coaster, number one would not make sense. In position number one, if your velocity is going, is going in this direction here, and your acceleration is going in that direction, that means you're slowing down. When V and A are opposite each other, it's going to slow down. So you can think of blood flowing. If blood's slowing down in that point, maybe you have a clogged artery right there, and that's slowing down your blood flow. And then when it rounds a bend here, when maybe it's going through a capillary bed between an artery and a vein, and you're going through this capillary bed, blood's flowing this way, and it's going to flow up that way. Well, right at that change, right where they change when they're perpendicular, that means the vectors change in direction. That means our velocities change in direction. And that's what we can see here. If we're slowing down here, then we're rounding the curve. So we're slowing down and then rounding the curve, that's change in direction. And then now we're in this vector right there. So if we had another vector that was just right along this tangent right here, if it was this tangent right there, we would say speeding up, and we would have V and A in the same direction. But right here, we're rounding the curve again, so they're perpendicular. So perpendiculars change in direction. And now V and A are in the same direction, so that means they're speeding up. So when V and A are in the same direction, velocity is speeding up, and so is acceleration. When your acceleration is getting greater too, or your velocity is getting greater at the rate of a constant acceleration. And then when V and A are perpendicular, it's changing direction, and when they're opposite, they're slowing down. So here's our summary. And of course, if you have any questions, please do feel free to reach out to me.